So let's turn our attention now to talking about neurodevelopment and neuroplasticity. Um, we're going to begin where I think a lot of you would probably expect we're going to begin, which is going to be in terms of both prenatal and postnatal development. In this case, prenatal development just referring to development that occurs in the womb, and postnatal development meaning everything that occurs after you're born, with most of our emphasis for sure going to be on postnatal development. But I do want to just say a few things about prenatal development. So I think it goes without saying that a lot goes on during prenatal development. Obviously, you go from a couple cells to, a newborn baby in approximately 40 weeks. And so you start with basic cell division, and then by the time you're born, you've got a head and arms and legs and a lot of things that have already taken place within your brain before you even come out of the womb. Now, it usually takes about 40 weeks, but actually sometimes premature infants can survive as early as 23 weeks, 28 weeks. A lot of times they will have various forms of neurodevelopment disorders, but not as often as you might necessarily think. So the question, of course, to consider is, well, while you're in the womb like this, what exactly is happening in your brain during this time? And to be honest, we could spend just so many days and weeks going over this stuff about what's going on in terms of genetic processing and mitochondrial DNA. We could go and talk about what happens due to emotional dysregulation in the mother. We could talk about what happens during nutrient intake in the mother. There's any number of things that we could talk about neurodevelopment in terms of prenatal development. So there's a lot to be said for sure. But to kind of keep it in line with the level of issues we've been talking about in this course at a sort of macro cognitive neuroscience scale rather than a more systems neuroscience scale, which is what a lot of this stuff is here. I thought that what we would do is just talk for a bit about certain things that happen in the third trimester in particular. So there's actually, I just thought this is really interesting. We're showing you a burgeoning field of prenatal fMRI, where people create these custom coil sequences that allow you to actually measure brain activity of an infant while they're in the womb still. So in this particular case, this woman is very pregnant and is going to be going into the scanner, not to get her own head scanned, but to get her fetus scanned. And so typically for many years now, there have been ways that you could do fetal MRI. So you can just see what the fetus looks like here. There's the brain, the spinal cord, and so forth. But this is actually taking it a step forward to look at fetal fMRI. There's not really a whole lot we're going to talk about, but I just wanted to let you all at least know that this exists, where people can look at the functional activations of the fetal brain even before they've come out of the womb. Hopefully in a couple of years, there'll be some interesting results that I can include in a lecture like this one. But for now, I do want to talk about just some results that come pretty much just from fetal MRI, and focusing on in the last trimester, that one of the big things that changes in the brain during the last trimester in the womb is this thing that's referred to as gyrification. And so here, what you can see is just the head shapes and the brain shapes of these fetuses at different points when they're in the womb. And as neurons start migrating to the cortex and start moving and getting in place, what starts happening is this complex folding, which is just a term that in neuroscience we call gyrification. The sulci are the dips, the gyri are kind of the peaks of it. Those patterns of gyri start to really develop. Lots of cortical connections are established, and during that, the brain starts to kind of fold itself into the way that it will ultimately be folded when it comes out of the womb, because it actually turns out that the major gyrification patterns in newborns who, right when they are born, are very, very similar to the adult brain. So it actually turns out that if you track the brain development of fetuses while they're still in the womb, you can see that as late as 7 months, there's really not a tremendous amount of folding in the brain, but pretty quickly as the brain expands, you can see a brain that starts to look pretty familiar. So for example, right here, this sulcus that we've seen, which is called the septal sulcus, it's the division between the frontal lobe and the parietal lobe. So somatosensory cortex would be here in the parietal lobe, motor cortex would be here in the frontal lobe. You can see this division here really extending for the temporal lobe. And so really what you can just see is that one of the major organizing principles of your neuroanatomy, namely the gyri existence, really seems like it's really developed in this last trimester. And it's partly thought that during this massive cortical development, that's when some learning actually occurs in the womb. So it actually turns out that when infants come out of the birth canal, they actually are not a complete blank slate. They actually have already picked up some patterns, some knowledge. And I think this is the type of thing that will be explored going forward with infant fMRI. But right now it's mostly explored, or actually almost entirely explored, with behavioral studies. So I talked to some of the discussion groups about this, so I'm going to tell you a little bit about it now just so you can see the data. So this is an experiment that they did in Sweden and the United States. And what they would do is they would get these babies who were just over a day old, so approximately 33 hours after birth on average, so really, really little babies. And what they would do is they would play these infants, these Swedish infants and these American infants, different sounds, different vowels in particular, because there's some vowel differences between Swedish and English. So if you're an American English or American infant, you've been hearing English vowels while you've been in the womb, but not Swedish vowels. If you're a Swedish infant, you've been hearing Swedish vowels, but not English vowels. And so what they wanted to determine is, could these really, really young babies differentiate between these vowels that they were exposed to? And when I say exposed to, what I mean is literally like while they're in the womb. The womb is not soundproof. If you were to stick a microphone, into someone's belly, you would actually, and like there was talking, even though the microphone's in someone's belly or in the, what's it called? The placenta, the fetal sac, I don't really know what the appropriate term is actually, sound does get through. And so the idea is that maybe while the infant is in the womb, maybe their brain is processing information from different sensory modalities. And so therefore they have some understanding of the difference between sounds that they are familiar with and sounds that they're not familiar with. And so on the vertical axis here, you can see this thing that I've called sucks per stimulus. So basically what's going on is that a kind of principle that people understand about newborn infants and young babies in general is they're curious. They like to see things that are new and different to them. So in visual studies, if you flash the same stimulus to a baby again and again and again and again, after a little while, it'll get bored and it'll like look away. But if you then flash a new stimulus that it hasn't seen before, its attention will like kind of spring back to life. So they took advantage of this fact by basically making it such that every time the infant would suck on this particular pacifier, it's linked to this auditory system. That's what's on the different sides of its head, such that every time it sucks, it will hear sounds. So if it's a sound that the infant is familiar with, it'll hear it a few times, get kind of bored, it will stop sucking, it doesn't care. If it's a sound that's new and interesting, once the infant makes that connection of, oh, when I am sucking on the pacifier, I get to hear more, I want to hear more, so I'm going to suck more. So the idea is that you can basically see how much sucking of the pacifier the infant does to hear either new sounds or old sounds as a function of, are they a Swedish baby or are they an American baby? And so here I will share the computer sound so you can actually see the correlation between when the infant makes the sucks and the sounds that you hear. Hopefully this works. Okay, so now what we can do is we can just look at the data about how often the infants are sucking. And what you get is data like this. So let me walk you through this real quick. If you are an American infant, you will suck more to hear Swedish sounds than to hear English sounds. English sounds are kind of old news for you. You've been hearing them while you're in the womb. They're not that exciting, that interesting. Swedish sounds, you've never heard those sounds before. They're a little more interesting. You want to explore that, so you're going to suck more. Swedish infants, you're going to see the opposite. They're now going to be more interested in these English sounds, and so they're going to suck more than it is going to be for the Swedish vowels, okay? So again, the idea here is just that it seems as if these infants are already behaving differently when they're just over 24 hours old, based on the sort of learning that they've been able to do in the womb entirely. So yeah, we're measuring this sort of behavior postnatally, but the learning presumably is happening prenatally. Okay, so even though that learning is happening prenatally, let's talk for the rest of the time, really, at least talking about development, about postnatal development, and specifically about the sort of changes that occur at birth. So after birth, even though the brain has a lot of the folding, and even though the brain is very well developed in many respects, the brain does certainly continue to grow very, very rapidly. So what exactly does that mean? How is the brain growing? Which parts of the brain are growing? What kind of structures are growing, and so forth? So there's this rapid increase in the brain that you can really just see that's particularly focused early on. So I just want to draw your attention to the fact that the reason there's this sharp line here going up is because this is prenatal development. But then once you are born, which is what this line is, there is continued to be serious postnatal development for a couple years that then sort of plateaus as you get older and older, okay? So what is causing all this growth exactly? Now, common sense would probably say, and I think it's a really natural and intuitive idea to have, that you're probably born with far fewer neurons than you end up with. That if you end up with 86 billion neurons, which is a number we talked about at the very beginning of the semester, maybe you start with 20 billion neurons or a billion neurons. And I think the logic is just that, look, like much like you grow muscles and skin as you grow up, your bones get bigger, your muscles get bigger, your hair, all these different things get bigger. You probably grow tons of new neurons, right? You grow hair follicles, you grow new teeth, you grow all these new things. That's probably what's going to happen in the brain, right? And to a very limited degree, yeah, that is true. There is this process that is called neurogenesis, which is literally the generation of new neurons. But here's the interesting thing. It's almost entirely in utero. It's almost entirely done while you're actually in the womb. So actually when a baby is born, they have like a vast majority of their neurons already in existence, okay? So if an adult has on average 86 billion, I mean, I don't know the exact number, we could look it up, maybe 75, 70, 80 billion. So not as many as an adult, but like a large majority of these neurons are already in existence by the time you're born. They're developed, they grow in utero. But the brain does continue to grow after birth, okay? You do see that there is still this increase in brain volume here. So what's going on? This leads to a natural question. What is the most drastic change in your brain that causes this extreme expansion if it's not the formation of new neurons? Turns out that it's not the formation of new neurons in general. It's a process called synaptogenesis, so not neurogenesis. And synaptogenesis is just the increase in the number of connections between the neurons via these synapses. So it's not that a neuron will spring into existence that didn't exist before, it's that that neuron will create a lot of connections with other neurons that didn't exist before. And so for example, here, you can just see there's a lot of these neuron structures here, but they're kind of isolated. They're on their own, these little black lines or neurons that aren't really touching much. By the time you get to a 6-month-old, by the time you get to a 2-year-old, you can start to see this is a much more dense array. And it's not necessarily because more neurons are springing to an existence, it's because they're each forming connections. And so actually, if you just look at what a typical neuron potentially looks like in the neocortex, what you can just see is that they start out relatively simple when they're first born. By 2.5 months, they're, 2-3 times as more complex. By the time you're 2.5, more complex even still. So it's the same neuron as it was before. It's just developed a lot of these connections. And this happens at an amazing rate. It actually turns out that during the first 3 years of life, the brain of a child is developing like hundreds, almost 1,000 connections per second, okay? So it's this rapid expansion in terms of the number of synapses and the number of connections between these neurons. So in addition to forming these new dendrites and in addition to forming these new synapses, whenever you create new synapses, you're going to create new myelination, okay? Because remember, and we talked about this a long time ago with neural communication, every neuron's dendrite is wrapped in this myelin sheath, which allows signals to travel much faster. It provides insulation. Notice over here, the signal moves slowly and then eventually it dissipates. Over here, it's wrapped in this nice insulation. It travels much faster. It gets to the bottom of the brain or the bottom of the neuron much more safely. We've talked about how, I think I mentioned back then on that day too, how certain neurodegenerative disorders such as multiple sclerosis, actually one of the things they do is there's this decay in this myelin sheath, which means that the neurons can't process information as effectively. So it actually turns out that as these new connections are growing, what you actually see is there's also an increase in this myelin that's wrapping around those dendrites. And it turns out that, remember, white matter that we can look at in MRI is myelin. Okay, so here we can see the corpus callosum, big white matter structure. And then here above it, we can even see this boundary between this white matter here and the corpus callosum with this fine-grained little bit of gray matter there. So there's a massive expansion in the connections, and then there's a massive expansion in white matter because of the myelin that's insulating those connections. And it actually turns out that when you look at brand new babies or newborn babies, you really can't tell the difference between the white matter and the gray matter. It all kind of bleeds together. It doesn't really differentiate as well. And then as the baby gets a little bit older, you can start to see, oh, okay, there's some stuff here, maybe around the corpus callosum, some white matter myelination. You could even see a little hint of it back here. By the time you're, a young toddler, you can really start to see some white matter connections form. And then by the time you're an adult, you can see a nice delineation between gray matter and white matter. You see that over here in this adult brain that you really don't see over here in this infant brain. And if you use a method like DTI, which gives us a bunch of plots like this, you can really see that, okay, sure, there are some connections there in a 2-week-old, but by the time you get to 2 years old, it's a much more intricate, densely populated array of white matter structures. Now, here is the interesting thing. As the brain grows and grows and grows to make these new connections and it increases its myelin accordingly, this thing that happens is that the brain will make too many connections, okay? It'll go a little overboard. And in that situation, there'll then be a process that's referred to as synaptic pruning. And what happens with synaptic pruning is something like this, where what you'll start to see is that there's this rise in the connections and then this pruning, this decrease, this fall in the connections, okay? So notice from 2 years old to 3 months old, big difference in the number of connections. From 2 years old to 6 years old, again, pretty big difference in the number of connections. A lot of this stuff has sort of been cut out, weeded out, whatever term you want to use. Now, why would it be a good idea for the brain to prune these connections? Why would it be the case that once you get this densely intricate web of neural connections in the brain, you want to actually scale it back a little bit? The answer is mostly for a couple of reasons. One is efficiency, and the idea there is that it's about, if you're trying to connect a motor system to a language system, maybe you don't need all these connections. You can actually, focus on certain connections that are much more useful. Those are the key ones. Let's focus on those. Whereas these other ones, they're not really as necessary. And you know what? Let's get rid of these unnecessary ones to lower metabolic costs. So it's an efficiency type thing where once certain skills, abilities, and connections have been created, the brain will then prune back the things that are a bit superfluous because they're not really needed anymore. Now, a question to wonder is if this formation and destruction of synapses through neurogenesis and synaptogenesis and synaptic pruning, if that occurs equally across the entire brain. And the answer is certainly no. Different systems develop and expand and contract at very different times. So in the textbook, there's a figure that looks something kind of like this. And the way to just read this is it's about the development in terms of the synaptic formation and pruning in different regions. So if you can see, there's 3 main things that are getting plotted. One is sensory motor cortex. So your motor system develops. It could be actually not just sensory motor cortex. It could just be sensory cortex more broadly. So it's about touch and motion type of coordination. It could also be about things like vision and audition. Those things develop very early. Then you have parietal and temporal association regions, which are related to things like the temporal lobe, where language regions are, for example, the parietal lobe, where attentional regions are also. And then the prefrontal cortex develops, which are involved in things like cognitive control, social inhibition, all the sorts of things we actually talked about in the social and emotional neuroscience lectures. Now, to give you some intuitions about why these 3 things are rising and falling in the way that they are, I want you to just take a second and think about little newborn babies, okay? So newborn babies, they go through certain developmental milestones. And speaking very broadly, they come out and after, not a lot of time, they can see and hear things around them. Then a little bit later, they can understand and they can talk and they can start to say things and have conversations with people. But only much later do they have cognitive control. Do they have control of their emotions? Do they have control in understanding social dynamics? Do they have control in inhibiting certain desires? So for example, this is my niece and my 2 nephews, and she's the oldest, and then there's the middle child, and then the youngest one. And if you think about it, the baby, he can see things around him. He can hear things around him. He can't talk. He doesn't understand what you're saying. He's a little guy. He's like 6 months old. He doesn't really know what's going on around him. Whereas him, he's about 4 years old. He can talk. He can have a conversation. If I tell him, hey, Elliot, go find the Hulk costume. Let's see if you want to be the Hulk for Halloween. He runs and he finds the Hulk costume, okay? But he has much less like social knowledge, social capabilities, and control capabilities relative to his big sister, who is now 7, can understand things around her, can understand other people's goals, their intentions. And so we can see that, we can see that reflected in the rise and fall of these different areas. These basic perceptual systems comes on, basic language and attentional systems come on, and then more experience dependent things about social cognition, emotional regulation, and so forth, they come on, okay? Now, this is here talking about, up until this point, we have been talking about white matter. I do want to stress, though, that white matter is certainly not the only thing that grows during development. You do get some bit of gray matter thickening, where literally if you kind of measure the size of the gray matter, if you delineate the boundary between the white matter and the gray matter, you actually can just quantify how thick it is. And you actually do find that it does thicken as you get a bit older and a bit older for a little while as a child. Gray matter thickness, just kind of interesting fact, is also associated sometimes with expertise. It turns out that, for example, if you're a super recognizer, if you're a person who's like, you know, in the top 1% of the 1% of recognizing people based on their faces, you find that the gray matter in your FFA thickens. And part of the reason that it's thickening is because as these connections between these neurons are getting established, even though there's not new neurons, you just see that there's going to be more stuff there in the gray matter. There's going to be more support cells, more connections there, and all these different things. So you can track gray matter thickness actually in the cortex as well. But then interestingly, it does start to actually go down, and it starts to go down very early. You might think that gray matter is going to start to decline maybe way later in life, in your 40s, 50s, 60s. It actually turns out that in the same way there's synaptic pruning, there is a bit of gray matter pruning. And actually, to give you a sense of this more broadly, I just want to point out the fact that this blue line is supposed to be in reference to males, and the red line is in reference to females. A question you might wonder is, why is it the case that the blue line is higher than the red line? And it's simply because, on average, males are bigger than females. It has nothing to do with cognitive capabilities. It has nothing to do with intellectual complexity. It has nothing to do with neurocomplexity. It has nothing to do whatsoever with intelligent capabilities or anything. It's literally just like a size thing. In the same way that adult men have larger feet than adult women, like they also have bigger brains. It doesn't mean that one set of feet is better really than the other. It just means that there's a difference between the genders in terms of size. And actually, to break this down a little bit more, I've actually plotted here now gray matter in the frontal lobe and in the parietal lobes. And there's a couple things I wanted to point out. And most notably, the biggest thing I want to point out is these arrows here that are showing you the peaks for when the females' gray matter peaks. And then that's what we see over here on this dotted line as well, compared to the males. Now, what do we notice between the difference between males and females? Well, what we notice is that females in both the frontal lobe and the parietal lobe seem to peak earlier. I'm sure a lot of you have heard this idea that female humans mature faster than male humans. A lot of girls will hit puberty before boys will. We can even see this sort of reflected in here when scientists and developmental psychologists and neuroscientists talk about females developing faster. It's an example like this. You can actually see this in their brains, that the female gray matter will reach its peak, let's say in these cases around age 10 or 11, whereas for the males, it's closer to age 12 or closer to age 13. So while gray matter rises and then falls, like we're seeing in this plot here, white matter actually turns out to be a different story. White matter actually continues to grow in its trajectory. It actually doesn't have the same amount of waning. So it's a little counterintuitive, I realize, because while there is synaptic pruning, there isn't really white matter pruning. Because, for example, the corpus callosum, a huge white matter structure, continues to link the different areas of your brain as you get older and older, as you learn new skills, as you acquire new knowledge. A lot of that is not coming from the creation of new neurons, it's coming from the creation of new connections and new links between different parts of your brain. So even though the neurons themselves and the gray matter and all those things might get pruned back a little bit, the white matter actually continues to grow. So it seems as if during early childhood, your brain spends a lot of time wiring and rewiring itself. It creates these connections, it cuts them back, and all these different things. So a natural thing to wonder is what exactly does your brain need then to develop in this normal way? If it's going to create these connections, if it's going to expand in this way, what needs to go on? And the simplest way to think about it is that these brains need healthy, normal, typical input. And so a lot of the initial studies that were done about neurodevelopment were done, as you can imagine, in animals. And they would do things like divide animals into different groups. One animal would be placed in a really enriching social environment with other animals. They'd be placed in potentially even rich physical environments where there's toys to play with, things to climb. Sometimes they could actually give you one without the other. They could put you in a social environment, but without many toys to play with. So it's a bunch of animals in a box. Or they could put you in a physical environment with no social stimulus. So it's like, I'll put you in a big box like this, but there's no one else there. Or they can just put you in a box by yourself where it has neither physical nor social stimulation. And it turns out that the animals that are in this top section up here that have more typical healthy and enriching stimuli to come in, when they have that more stimulation, both social and physical, they actually will develop more connections in their brain. They'll have more neurodevelopment in general. They'll have greater problem-solving capabilities later in life. You could put these animals in a maze that they've never been in before. They're going to figure it out faster than these animals here. And so you really can see that when you deny these animals the opportunity to kind of get stimulated through social interaction, through physical interaction, and so forth, it really can impair a lot of their general neural and cognitive capabilities. To give you an extreme example of that, let's watch this video. Some of you might have seen it with me before, but let's just watch it again about a kitten who is now not only deprived social and physical interaction, but was deprived normal visual input. It was raised in a situation that it didn't get to have the normal sort of visual perceptual experiences that most animals will have. So let's give this a shot.
In these experiments, we regulate the visual environment by keeping kittens in complete darkness from birth, bringing them out for periods of controlled visual experience inside special cylindrical chambers. Here, a kitten is being exposed to an environment consisting entirely of horizontal stripes, and it wears a ruff to prevent it seeing its own body. This particular kitten will be exposed to these stripes each day from the age of 3 weeks until it is 3 months old. All the rest of the time, it remains in complete darkness. What are the consequences of this restricted visual experience? This is the same kitten at 3 months of age, seeing a normal environment for the first time. If we test its visual ability at this stage, we find that unlike a normal kitten of the same age, it has no visual placing reaction. It does not extend its paws to reach a surface below, although it does so as soon as it touches the table. And whereas a normal kitten backs away if an object is suddenly thrust towards it, this animal has no such startle reaction. It does not even follow a moving object, unless this makes a noise. These initial deficits seem to be failures of visuomotor coordination, probably an effect of the kitten's lack of interaction with visible moving objects, rather than of its specific exposure to stripes. However, these gross problems don't last, and within a few hours, the kitten seems almost normal. Now, after several days of living in a normal environment, it has typical visual placing. It shows startle reactions. And it follows a moving object.
Okay, so what we can see from this particular kitten is this idea, again, that you need healthy, typical, normal input to develop these things that are pretty basic. If you want to be able to see normally, you want to be able to hear normally, you need to have good sensory stimulation if you're going to develop those capabilities. And then obviously later, if you wanted to be able to develop social abilities and those sorts of higher level types of functions, you also need input like that. But rather than skip to that sort of level, I just wanted to tell you about one more study that was looking at face patches and face deprivation. So this was another type of study where you take animals and you can raise them in a very controlled environment. It's referred to as controlled rearing. And in this particular case, what they did is they raised monkeys since birth, but they never let the monkey see a face, okay? So every time the experimenters would come in to interact with the monkey, they would wear these like fencing sheer masks, so you couldn't see their face even though they could see. But the monkey could see your hands, the monkey could see your body, the monkey was given lots of toys to play with. It was in, an environment, they tried to spruce it up a little bit to make it nice for the monkey. But the monkey never, ever, ever, ever saw a face, okay? So the question is, if you then put a monkey in a scanner and for the very first time, you show it a face while it's getting scanned, what is its brain gonna do? Is it gonna have face patches kind of like the FFA that we see in humans or not? So the answer looks kind of like this. So these gray things here are flat maps. So this is the monkey's brain. It's just been, instead of being folded up, it's just been flattened out, okay? And in a typical monkey, this is how you can see their face patches. So if you look at the response of faces greater than objects, their V1s back here, their frontal lobes up here, these little patches right there, those are their monkey face patches. So we can see in these three particular animals that had typical environments raising up, they all had face patches. If you look in the comparable regions in these control-reared monkeys that had never seen a face before, they don't have these face patches, okay? So again, for something even as specific and selective as a face patch, which we've talked about at length, you need to have the typical development. Even though it seems like our brains may be potentially biologically predisposed to do these things, if you don't give the system the correct type of input, it's not going to be able to develop accordingly. So a question some of you might be wondering is, well, how could you study this in humans? And as you can imagine, it's really, really difficult. You can't do face deprivation with infants. You can't raise infants in darkness. You can't run these experiments on human children for a variety of reasons. So the best data that people have come from these extremely tragic cases where people are abused as their children, where they are abused as children. And they can then later study these people once they've been saved and see what capabilities these children do and do not have. So the most famous of these examples is certainly Jeannie, who I'm sure many of you have heard of. She, from a very young age, I think just a couple months old perhaps, was placed in a straitjacket in the basement and was tied to a toilet. The only person she ever interacted with was her abusive father, who would come down to give her food, but would not interact with her, didn't speak to her, didn't play with her. She pretty much just sat there all day, every day, except doing nothing except for eating when he would come down to give her food. By the time she was found at age 13, so she was down there for many years by herself, she was, I believe, about 59 or 60 pounds, whereas a girl of her age at that time in American history, this was many decades ago, would be about 100 pounds. And so she was severely malnourished as well. And there have been a lot of studies about Jeannie and the things she couldn't do. In part two of these lectures, I'll talk to you a little bit more about her. But the other situation I wanted to talk about, and this is mentioned in the textbook, is about these children who were placed in these orphanages in Romania, because back in the, oh gosh, when was it, the 50s or the 60s, Ceausescu, who was the leader of Romania, implemented this order that birth control and abortion were both outlawed without any exception whatsoever. And the idea was to raise capital. The idea that he had was, if we have a lot more citizens and a lot more people, we'll be a much more larger population, we'll have more power, we have more of a workforce, we have more military. So his idea was increase the number of people, increase the amount of Romanian clout. Families were fined if they had fewer than 5 children. So if you were of a certain age and you had been married for a certain amount of time and you did not have 5 children, you would be fined. Gynecology exams became mandatory at work. If you wanted to have a job, part of keeping your job was to have monthly gynecology exams to make sure that people were fertile and to keep track of who was of like a childbearing situation, and to make sure that people had not gotten pregnant and aborted those pregnancies. So if the gynecologist had noticed when you went in for your exam that there was evidence of an abortion, you could be fined or imprisoned. And so what people did, though, is they studied a lot of these children as a function of whether or not they stayed institutionalized compared to other Romanian children who were not institutionalized. Oh, one thing I should have mentioned is the reason that there was this, these orphanages were overrun and there was this much institutionalization is because with these pretty extreme anti-abortion, anti-birth control type of measures, a lot of families just were unable to support or take care of their children. There was a lot of poverty in the country. Sometimes parents would die. And so a lot of children ended up in these orphanages that were just completely overrun, and the children would be placed multiple in a crib, and they would have like one caretaker for like 80 babies. And so they were really isolated. They were not getting any sort of normal, typical development experiences. They were not getting spoken to very often. They weren't getting exposure to social stimulation from adults and so forth. And so what they wanted to do is look at how did these children develop as a function of their institutional history. So they would look at children who were institutionalized for many, many, many years, up until about 4 months of age. Children who were institutionalized, but they were placed in foster care after they were 2, so as a 2.5, 3-year-old. Children who were institutionalized but placed in foster care before they were 2 years old, so placed earlier than these children, compared to other children who were not institutionalized ever. And what they could see is that, sure enough, there would be these major developmental issues with these children who were denied these sort of neural stimulants that they normally need. So children who were never institutionalized on average had a DQ, or it's comparable to an IQ. It's a developmental quotient rather than an intelligence quotient. If the average is about 100, you can see this sort of gradient effect where children who were not institutionalized seem to develop normally. Children who were fortunate enough to be put in foster care, they had a little bit of a deficit, but not nearly as much as children who were institutionalized for many years or didn't get out of those institutions for many, many years. And it actually turns out there have been a lot of subsequent studies about these Romanian orphanages, and people have still continued to study these children after many decades and how they're now adults. And they have actually found that in a lot of these cases, really tragically, a lot of these children who didn't have any typical development during this first few years of life, they still seem that on average they have certain developmental disabilities relative to their to comparable children who weren't in the same type of situation in these orphanages. So this is why I've been talking about this idea that children's brains are rapidly getting wired up during this period of life, but they really critically need the right sort of input. And if you deny a child that sort of input, if you deny a brain that sort of input, it's not going to be able to develop in a normal, typical way, not only for things like intelligence or social capabilities, but even for things as basic as vision. Remember, like that cat that we saw a little bit ago. So during youth, when the brain is naturally forming and destroying and perfecting these new connections, it seems as if it can really restructure itself. It can develop the capability to learn these things. It can develop face patches. It can develop the ability to start to understand language. And it's because during this period where the brain is really creating and forming and destroying these neural connections, you have this massive plasticity of neuro reorganization. That's what I mean by plasticity, during this period that we refer to in the literature as a critical period. And so I think we will take a break there. And when we come back for part 2, we'll dive deep into speaking at length about critical periods, massive cases of neuroplasticity, when they stop, how extreme they can be, and so on and so forth. All right, so come back soon.